All right, so this is the first of two lessons looking into Voronoi diagrams, which are named after a Russian mathematician whom I'm probably mispronouncing his last name, so sorry any Russian speakers out there. But we actually were introduced formally to a Voronoi diagram at the end of the last lesson, and now this is the focus of it. So let's make one. So a Voronoi diagram is one in which we show all the regions in which the areas within the regions are closest to some specific point. So right now, this is a very simple Voronoi diagram in which there's 2 points, A and B, and everything on this side of this dashed line is closest to A, everything on this side of the dashed line is closest to B, and that dashed line is the perpendicular bisector between A and B. And when you have only 2 points, a Voronoi diagram is simply just a single perpendicular bisector, and that's it. Gets more complex when we add more than that. And so now we have a third site, point C, which is at -3, -1. So let's show that. And that is right here, and I'll label that as point C. Actually, I'll be more creative and make it green. Ooh, that looks good. All right, so now clearly I have to adjust this diagram because, you know, this line here doesn't separate all the regions properly, although it does have aspects of it that are still going to be kept. And so to figure this out, I first now need to figure out 2 more perpendicular bisectors. I need to find the perpendicular bisector between A and C, something that looks roughly like that. I need to find the perpendicular bisector between C and B, something that looks roughly like this. Now, those sort of rough visuals of things are quite helpful, I think, but eventually I want to find the actual perpendicular bisectors. Now, in this case, we can do everything visually because I have a detailed graph and the slopes of everything are actually quite pleasant. So first, let's look at A and C first. To find the perpendicular bisector between A and C, I need to find the midpoint between A and C, which, keep in mind, if I draw the straight line from A and C, the midpoint I could find by finding the average of the x and y coordinates. In this case, I can actually see it, and it's always good to double check, but this point right here is the midpoint of AC. And so now I can find the perpendicular bisector of AC. It must go through that point, but it must be perpendicular to that line I just drew. So now I need to look at the slope of that line I just drew. And the slope of this line is, it goes down 1 over 3. Sorry, down 3 over 1. So the slope of that line that joins A and C is -3. Therefore, the perpendicular slope is going to be the reciprocal of that. Maybe I'll write this separately. So the slope I want to look at, the perpendicular slope, is going to be the opposite sign, so +3, and the reciprocal, so 1/3. So I can visualize now this perpendicular bisector quite nicely, and I'll do this in orange. So from that point right here, I want to visualize a slope of 1/3, so up 1 over 3, which means another point must be right here, and another point must be right here, or I can go backwards, down 1, backwards 3. And so what I have now is one of the 2 perpendicular bisectors I need to show. And I'll draw it as another dashed line. Keep in mind, if these values weren't quite so pleasant, I'd have to maybe rely on a bit more numerical work, but I can visualize these things quite nicely. So same idea now for CB. So I'm going to erase this just to clean that up. Same idea here. First, let me visualize the line that connects AB. I can see the midpoint right now, but if I wasn't sure, I could again find the average of the x values between C and B, average of the y. The midpoint is right there. I now need to visualize the perpendicular slope with accuracy. First, the slope of CB. I can see it goes up 1 over 2, so slope of 1/2. Therefore, the slope of the perpendicular line will be -2, which is -2 over 1. So down 2 over 1. So I'm going to draw that. So again, from this point, I can go down 2 over 1, or I can go up 2, backwards 1. Either way, I can now visualize this perpendicular bisector quite nicely. All right, so now let me just clean this up. All this work I did was great, but I don't want to things get too messy. Now this is pretty much identical to the end of the last lesson. For example, this point where all 3 of these bisectors intersect, that is the point that is equidistant to A, B, and C. So now what are my boundaries? Well, for example, I'll use my highlighter for a moment. This region here is still a boundary between A and B. But now, this becomes the boundary between A and C, and this becomes a boundary between C and B. And so what I've basically highlighted in green are my boundaries of my Voronoi diagram. So I just want to make these a bit more clear. I'll make them a bit darker here. But then I'm essentially done. So that, and this are my boundaries, which go on indefinitely. And I can now erase these here. Maybe I'll erase this. There we go. So now I have my completed Voronoi diagram. Keep in mind this point right in the middle that I'll highlight in orange. That is the one point that is equidistant to A, B, and C. Everything else, for example, in this region here, everything in that region is closest to B, and we've seen similar things from before. All right, so what I have this time is another 3-point Voronoi diagram, but the information given is a little different. I give us the coordinates of A, which are -4 and +2. So I'll label that here. Other than that, I just give the midpoints. For example, the midpoint of AC, I say, is -1.5, 2.5. So that means the point halfway between A and C. It must also be on this perpendicular bisector here. So I can see where it is. And so I can see the coordinates, -1.5 and 2.5. So how can I use that now to find the coordinates of C? Well, we did something very similar back at the beginning of the geometry unit with three-dimensional space quite often, in which if I can figure out how to go from here to here, I can just do that one more time from here to here. So what do I mean by that? Well, for example, as I go from A to the midpoint, my x values go from -4 to -1.5, which means my x values increase by 2.5. So I need to do that again. To go from here to here, my x values will increase by 2.5. I think, what is -1.5 plus 2.5? That is 1 whole. And then the same idea for my y values. If I look from A to the midpoint, it goes from 2 to 2.5, so it goes up by 1/2. So it should go up by another 1/2, and now it should be at 3. So now I know the coordinates of C. And I can do the exact same thing for A and B. The midpoint, again, is given. The midpoint is at -2.5, 0, so it's right on the x-axis. And same idea. Look at these, the difference from x and y. So from here to here, x goes up by 1.5, so it should go up by another 1.5. So now B is at -1. And same thing for y. Y goes down by 2 from 2 to 0, so it should go down by another 2. It should be at -2. Now I have all the coordinates that I need here. All right, so the last question is to determine the point that is equidistant to all three sites, the three significant figures, which is this point, like mentioned in the last question. It's this point right in the middle. So what are the coordinates of that? Well, if I maybe go back to my previous example, that point that I've highlighted in orange was equidistant to A, B, and C. It is the intersection between any two of these perpendicular bisectors. So if I can find the equation of any two of these perpendicular bisectors, which again, that's what these are, if I can find the equation of any two of them, I can then find where they intersect. And they're all lines. And so I'm going to focus on these two perpendicular bisectors here because I already have the midpoints for them. So I'm going to call this one here L1 for line 1, call this one L2. If I can find the equations of line 1 and line 2, then I can find where they intersect quite quickly. So how do I find the equation of a line? Well, to find the equation of any line, recall all you need is a single point, and I have the midpoint of each, and I need to know its gradient or its slope, which I can figure out fairly quickly. So let's look at line 1. If I want to figure out line 1, let me first, I'll kind of go back and forth here a bit. So for line 1, I first need to find the slope of AC, the slope of this line here, which I could use a slope formula. I could just look at my y values. For example, my y values go from 2 to 3, so I have a rise of 1, and a run from -4 to +1, a run of 5. And I'll do the same thing for L2. So for L2, I'm looking at, first I want to find the slope from A to B. And the slope of that, it goes, my y values go from 2 to -2, so the slope or the gradient is -4. My x values go from -4 to -1, they go up by 3. And so at this point, those are the slopes of not the perpendicular bisectors. These are the slopes of the lines between those points. The perpendicular bisectors will have a perpendicular slope to these. So for L1, I should say this 1/5 isn't really the slope of it. That's the perpendicular slope to it. So the slope of L1 is going to be -5, the opposite reciprocal. And for L2, that -4/3, I guess I really should say, is the slope of what's perpendicular to it. So the actual slope of line 2 will be +3/4. And now to find the equation of each line, I just need to pick a point, which again, that midpoint. And again, the midpoint for L1 was at -1.5, 2.5. And the midpoint for L2 was at -2.5, 0. And so now for each, I have my slope. For each, I have an x and a y value. For each, I can use that point slope or point gradient form to come up with the equation, which is in this form here. Y minus y1 equals m times x minus x1. So now this is going to come together pretty quickly, especially if I use my graphing technology to my advantage. All right. So for that first line, the one I'm calling line 1, the one up here that is highlighted in orange, I get y minus 2.5 equals 1/5 x plus 1.5, because I'm subtracting a negative. For the other, I get y minus 0 equals 3/4 x plus 2.5. I want to solve these by graphing, just because I'm visualizing a graph anyways. To do that, I just need to have y isolated, which it already is for line L2. So for line L1, I'm just going to add 2.5 to both sides. I don't even have to distribute anything. I'm just going to write it as y equals 1/5 or 0.2 x plus 1.5 plus 2.5. That can be graphed on any graphing device quite nicely. I'll just type it in exactly as it is. The other one is I don't have to change it. I just don't need the -0 anymore. So now I can solve by graphing here and find the intersection point. Before I go do that, other options would be to solve this algebraically, which would be significantly more work for no gain, so I would not recommend it on an IB assessment. Another option is you could put each of these in if you distribute and kind of put these into a more sort of a standard form, or I could then use the simultaneous polynomial equation solver. But again, I think all that would be more work than just solving this by graphing. And so I'm going to go to Desmos here. And what I've done first, just for a visual, is everything that was described before. You can see points A, B, C. The midpoints I've just plotted. So basically all I'm doing here is confirming that I was right before. And then here at the bottom are the two equations. So that was line 1 I've called. That was line 2. There was a third line. It doesn't matter, though. I just need to find any two of them. And where they intersect is right here. So the three significant figures, -1.20 and 0.978. And that is it. All right.